So next in chapter 9, we are going to look at polarity in a molecule. So it does turn out that you can have polar bonds, like for example, between oxygen and hydrogen. But it turns out that due to the arrangement of them, you can get the overall molecule to be nonpolar. So how do you know which is going to be which? Well, it all comes down to symmetry. So when we have symmetric molecules, the electronegativity pole vectors or dipole moments cancel out. Okay, so if you can get equal and opposite pole across the whole entire molecule, you get a non-polar. So all of those dipoles cancel each other out. If you don't have that arrangement, if you have asymmetric molecules, then the electronegativity vectors do not cancel out, and that molecule is polar. Okay, so let's take a look at a couple of examples that we have down here. All right, so we have our first one, our CO2. So CO2. So if you look at a periodic table, oxygen in that upper right-hand corner, much more electronegative. So oxygen is going to have a strong pull of electrons from that carbon. Same way over here. So even though this is a polar bond, because oxygen is far more electronegative, so we'd put a delta minus here, a delta minus here, and a delta plus here. But even though this is far more electronegative, because it's equal and opposite, this molecule here is nonpolar. Okay? So it ends up being nonpolar. What if we take oxygen away and replace it with a sulfur? So you can kind of see that this is symmetric. You have the same atom on each end. This is not. Okay, so this has a very strong pull, so we'll do it the same. Sulfur, not nearly as electronegative as oxygen, so it's going to have a very weak pull. So I'll make it a different color, and I'm going to make the arrow a lot shorter. So overall, you still have a net pull in this direction here. Okay, so this would be kind of what's happening net. If you were to add those two vectors together, that's what you'd have. So because it's asymmetric, this is pulling a lot harder than this is over here in terms of electrons. We get a polar molecule. Okay, so polar. All right, so it depends a lot on the shape we have. So our example here, we have NH3. I'm going to get to that in just a second. I want to do CH4 first. Okay, so this one we have the tetrahedral shape. So again, kind of recall what that looks like, that tetrahedral shape. Okay, so every single position on that tetrahedron is exactly the same. They're all hydrogen. So this one, the electronegativities are almost equal. So I'm going to kind of draw, there's really not a whole lot of pull in any direction here, because they're almost identical. So since all of those positions are the same, you get equal and opposite pull. Okay, so what that looks like, of course, if I attach hydrogens here. So put hydrogens on our molecule. We have this here, again, nice and symmetric. Everything on here is identical. Okay, what if one of these was different? What if I took a hydrogen off and replaced it with something like a fluorine or a chlorine? Then we would have something like this. Okay, is this symmetric anymore? The answer is no. So if we were to kind of draw this one out, we would have our carbon, hydrogen, 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 and now we've put a fluorine there. Okay, so very, very strong pull in one direction. And again, these aren't really pulling at all. So you can kind of just see it by looking at the molecule here, not symmetric. Okay, what if I put two fluorines on here? What if I put two of them? So what if I have this? So are you going to get equal and opposite pull of those two fluorines? Okay, if we look at that angle there, the answer is we are not. So even if I drew it on paper, We have the H, we'll put the F, the H, and the F. So they do kind of, on paper, look like they are kind of opposite. But remember, that angle is 109.5. That angle is this. They are not equal and opposite here. They are not canceling each other out. In fact, they're going to add together and make the dipole of this molecule, I don't know, something like that. Okay? So they will sum together, and the dipole moment of this molecule would be right in between them. So if you could split this bond with this pin here, the dipole moment would be right in between. Okay, so not equal and opposite here. Okay, so let's look at some different shapes. Okay, so let's go back now to this one here. So this one, what happens if it's a lone pair instead? Okay, so remember we talked about things having to be symmetric. So let's just put a lone pair here. You can kind of see having that lone pair kind of gives you this situation here. You have now nitrogen is more electronegative than hydrogen. So you're simply having nitrogen pulling from 3 directions. So pulling this way, and this way. But what's happening here with that lone pair? Well, if we kind of take it off, kind of remembering that there's really nothing there, there is no pull there. So there's nothing to pull in this direction. So this is pretty much an asymmetric shape. So we don't get a lot of non-polar with a pyramid shape, with a trigonal pyramid. And that's because the lone pair breaks the symmetry. There's nothing to put on the opposite side of that lone pair to cancel out the electronegativity. Okay? The only way this could be non-polar is if every single one of these atoms had the exact same electronegativity. Okay, so if these 3 and this were the same, then you could get non-polar. Other than that, it's always going to be polar because lone pair tend to break the symmetry. Okay, so that would be true if we had bent as well. So like water, okay, if we had H2O, you have the oxygen pulling, but nothing up here to cancel that. So the dipole would be right here on the center of that oxygen pulling up and away. Okay, so what about some other shapes? Okay, let's look at some other shapes. What about a trigonal planar shape? Okay, maybe you can kind of guess how this is going to go. We saw an example of carbonate. Okay, so we do know that this has resonance and that double bond is floating around and they're essentially all 1 1/3 bonds. So these are all identical. Okay, so if you have all oxygens on every single side here, just like this, nice and symmetric, this is going to be non-polar. Okay, so what if I take this away, this oxygen, and replace it with something else? Okay, so this one we would expect to be non-polar. What if we had this? What if I replace that with a hydrogen? Okay, what if I did that? Is this symmetric anymore? The answer is no. Okay, so you get strong pull this way, and you get strong pull this way. Since these are about identical, you don't really get any pull in either direction here. So you have 2 directions pulling and 1 not. So you're going to get an overall dipole pointing in between those 2 oxygens. So the overall dipole moment would be somewhere along this direction. Okay, so again, you can kind of see here, all identical, symmetric. They're all the same. And then here, when I put something else there, like a hydrogen, oxygen's hydrogen broke the symmetry, clearly not the same. Okay, so what about some of our more interesting shapes? So what about this shape here? Okay, so it turns out you can have some different scenarios here, and we call those isomers. So for example, we are going to look at PF2CL3. So PF2CL3. So it is going to end up being this shape right here. So single bond. So we can arrange this a couple of different ways. Okay, so let's take a look. We're going to have 1, 2, 3 chlorines, and we're going to have 1 and 2 fluorines. Okay, so this is going to be a trigonal bipyramid, okay, with no lone pair on the phosphorus. Okay, so you can see we can have a couple of arrangements. I can take these 3 chlorines and I can put them all in the same plane. So I can put them right here in the planar positions. So are they going to have equal and opposite pull with one another? The answer is yes. We saw it up here with this, so it stands to reason it would be the same here. So in this position, we'd have equal and opposite pull. What about putting the fluorines on here? If I put one on the top and one on the bottom, are they going to have equal and opposite pull? The answer is yes. So because it's linear between these 2 fluorines, we're going to have pull this way. That's going to cancel out the pull this way. And in the plane, we're going to have equal and opposite pull along all those directions. So in this variety, so if I draw this, what we call isomer, this one is non-polar because all of those canceled each other out. Okay, but I can draw another what we call isomer. An isomer is you have the exact same atoms, but you've arranged them differently. So what if I switch these? So what if I switched a chlorine and a fluorine? Does this look symmetric anymore? Hopefully your answer is no. So now this is not pulling equally to this. Fluorine pulls a lot stronger than chlorine. So you have overall pull towards the white one here. So same thing here. You're not getting equal and opposite cancel, like sort of canceling of the pull here. Fluorine is more electronegative. It's pulling a lot more. So in this isomer, so in this one where I don't have them equal and opposite, where I have different atoms in the plane and different axial ones, this version of this molecule is polar. So we have different ways we can arrange atoms to get polar and non-polar. Okay, so as you hopefully could imagine, the same is true with an octahedral shape. So the way I've arranged this one here, which for example could be SF4Cl2, for example. Okay, so if I put 4 of them essentially say in the XY plane, so these would be my 4 fluorines, and I put my 2 chlorines equal and opposite like I did here, you can see how this one is symmetric. The whites are all opposite one another, and the greens, the chlorines, are opposite one another also. So this arrangement of this molecule would be nonpolar. Could you arrange this to have a polar version of this? Hopefully you see this and your answer is yes. Okay, so we can put this one here. We can put this one here. So if we look at this one, we have these 4 fluorines on this side pulling a lot stronger than we do here. We don't have them equal and opposite to cancel one another out. Okay, so in this case, this arrangement would be polar. Okay, so we have 2 here, and these ones here. Again, not equal and opposite, not symmetric. So again, the key to all of this is symmetry. Not symmetric, but if I move just 2 atoms, I make it symmetric. Okay, green's opposite, white's opposite. So in this shape and in this shape, you can have different arrangements that will give you polar and nonpolar. So the same is going to be true if you have lone pair. So let's say we have this atom and all 3 of these that are green are lone pair. Let's say we have 1, 2, 3 pairs of lone pair. Okay, so if we take those lone pair away to get our molecular geometry, we end up with this. Okay, equal and opposite, in our linear geometry. So we could get non-polar with this by putting all of those lone pair in the plane. Okay, so same is true here. What if these green atoms were lone pair? Okay, we take those lone pair away. We end up with the square planar, where again, they're all equal and opposite. The lone pair would be sticking out this side and sticking out this side. So on these sides here, equal and opposite. So this would also be non-polar. Okay, so it just depends. For our tetrahedral shape, so for our octet shapes, if we saw over here, if you put a lone pair for something like this, or like we had with water, where we had the bent shape. So a lone pair on these shapes here pretty much automatically make it polar. There's no way to arrange anything in a tetrahedron to get things to be equal and opposite. Okay, so again, remember our tetrahedron had those 109.5 bond angles. So there's no way to get them opposite. Okay, so I have them kind of opposite here. They're not equal and opposite pole. So there's really no way to position things to get them to cancel like we were able to here, just because of the angles of the shape. So the same thing is true with something like this. If we had a lone pair, like for example with nitrite, so even if we had a lone pair there, so we had this shape with a lone pair, there's no way, again, these are both oxygens, but because of the angle, there's no way to get them equal and opposite. So you are going to have an overall net pull just because of the angles. Again, here we could get them equal and opposite. Here we cannot because of those angles. Okay, so for your shapes, your octet shapes like tetrahedron, like trigonal planar, and for those two especially, and then the shapes that go with it, like bent and trigonal pyramid, when you have lone pair, it breaks the symmetry of those shapes. So just kind of keep that in mind. For these, definitely you have to look at the different arrangements you can make to see if you can get them to be equal and opposite.